Hello learners! Let's start by tracing the journey from raw ore to shining pure metal. Think of this as following a recipe. Each ingredient and each step matters. Metallurgy has 6 main checkpoints: ore preparation, concentration, oxide formation, reduction, refining, and finishing. The path chosen depends mainly on the ore type, whether it's an oxide, sulfide, carbonate, or halide. Thermodynamics, especially Gibbs free energy versus temperature, tells us if a reaction is possible, while kinetics and particle size decide how fast it will happen. Fluxes like calcium carbonate or calcium oxide act like helpers, they capture impurities and form slag that floats away. And just like cooking with safety in mind, metallurgical plants must handle dust, sulfur dioxide gases, and hot slags carefully. Remember, the very first decision about ore class locks most of the choices we make later. Once the ore is mined, it's far from pure. Imagine buying rice mixed with stones, you would first clean it. Similarly, ores are concentrated before reduction. We start with crushing and grinding to free the valuable mineral grains from gangue. For dense ores like tin oxide, gravity separation works beautifully. Heavy grains settle while lighter waste floats away. For sulfide ores like zinc sulfide, we use froth flotation. Here, collectors like xanthates make ore particles water repellent, frothers like pine oil create stable bubbles, and depressants like sodium cyanide prevent unwanted minerals from floating. Magnetic separation is used for ores like magnetite and hematite blends, while leaching uses selective solvents. Bauxite dissolves in sodium hydroxide in the Baer process, and silver ores dissolve in cyanide solution in the presence of oxygen. The goal is simple: enrich the ore so that later stages consume less fuel, less time, and fewer chemicals. Now comes a crucial step: converting ores into oxides, because oxides are much easier to reduce. In calcination, we heat ores in the absence or limited supply of oxygen. For example, zinc carbonate on heating decomposes into zinc oxide plus carbon dioxide. The reaction is ZnCO gives ZnO plus CO. In roasting, we deliberately use excess oxygen. Zinc sulfide reacts with oxygen to form zinc oxide and sulfur dioxide. The reaction is 2ZnS plus 3O gives to ZnO plus 2SO. Lead sulfide shows an interesting sequence: 2PbS plus 3O gives to PbO plus 2SO, and PbO can further react with SO to form lead and sulfur trioxide. By the end, we have a porous, reactive oxide ready for reduction with volatile components like water, carbon dioxide, and sulfur driven away. Think of this step as preheating the ingredients before the final cooking. Here's the most dramatic part: turning oxide into metal. With carbon, the reaction is Mo plus C gives M plus Co, or Mo plus Co gives M plus Co. In the blast furnace, iron oxide is reduced by carbon monoxide. The key equation is FeO plus 3Co gives to Fe plus 3Co. Meanwhile, flux chemistry is at work. Calcium carbonate decomposes to calcium oxide and carbon dioxide. The calcium oxide then combines with silica to form calcium silicate slag, which floats on top of molten iron. Sometimes hydrogen is used. For tungsten, the reaction is Wo plus 3H gives W plus 3HO. This prevents carbon contamination. The aluminothermic or thermite method is spectacular. Chromium oxide reacts with aluminium, CrO plus 2Al gives to Cr plus Alo. The reaction is so exothermic that it produces molten chromium instantly, strong enough to weld railway tracks on site. Each choice depends on whether Gibbs free energy favors the reduction and what purity we want in the final metal. Some metals are simply too reactive to be reduced chemically. Sodium, potassium, calcium, magnesium, and aluminium all require electrolysis of molten salts. Take aluminium. Aluminium oxide, dissolved in molten cryolite, undergoes electrolysis. The reaction is Alu gives to a liquid plus 3/2O gas. The cryolite lowers the melting point and increases conductivity, making the process more efficient. For sodium, molten sodium chloride is electrolyzed in a down cell. We cannot use aqueous solutions because water would be reduced before sodium. Here, remember the equation delta G degree equals minus NFE degree. A very positive electrode potential means the reaction demands external electrical energy. In other words, for these metals, electricity itself is the reducing agent. Now that we have the crude metal, we need to purify it. In electrolytic refining of copper, impure copper is the anode, pure copper is the cathode, and copper sulfate solution is the electrolyte. At the anode, Cu becomes Cu superscript 2 plus 2 electrons. At the cathode, Cu superscript 2 plus 2 electrons become Cu. Precious impurities like silver, gold, and platinum settle as anode mud. For copper and tin, poling is used. Wooden poles release gases that reduce metal oxides, turning CuO into pure copper. Zone refining is used for semiconductors like silicon and germanium. A moving molten zone pushes impurities to one end. For metals like zinc and mercury, distillation or liquation is used, exploiting their volatility. The key idea is that the refining method is chosen based on the impurities present, not just convenience. Finally, let's apply what we've learned with a calculation. Suppose we want to produce 100 kilograms of aluminium by electrolysis. Moles of aluminium is equal to 100 divided by 27, which is about 370 moles. Each mole of aluminium requires 3 moles of electrons. That means 370 times 3 is equal to 1110 moles of electrons. Total charge Q is equal to NF is equal to 1110 times 96,485, which is approximately 1.07 times 10 coulombs. If our current is 50 kiloohms, the time required is Q divided by I, or 1.07 times 10 divided by 5 times 10. That gives about 2140 seconds, or roughly 36 minutes. The energy consumed at 4 volts is Q times V is equal to 1.07 times 10 times 4, which is 4.29 times 10 joules. Converting to kilowatt hours, that is about 119 kilowatt hours. This shows why aluminium is energy intensive to produce. Always link stoichiometry with the relation Q equals it, and don't forget the factor of 3 electrons per aluminium ion.